So, what is probability sampling? Suppose we have a population of size n, and so n is the population size, and the sample size is n, is your sample, and we take a sample of size n from it. Now there can be a number of distinct samples of size n then can be selected from this population. So S1, S2, Sk be this set of samples that are selected from this population. Each of these k samples are assigned a probability of being selected. Let sample Si be assigned a specific known selection probability, say Pi. So each of these will have a probability. So this one say will have probability of P1, this one will have probability of P2, and say Si sample will have a probability of P1, Pi. So obviously with the law of probabilities, the sum of probability I is equal to 1 to k, because there are k samples, Pi is going to be 1. This sort of sampling procedure is called as probability sampling, because the whether or not this particular sample Si is getting sampled from this population of n has a probability associated with it, a Pi. So that is why this sort of procedure is called probability sampling. Now what is the estimator? So we have a population will have some parameters, and these parameters we want to estimate using a estimator. The actual value of the estimate will vary based on the sample size or the actual sample chosen, but we know the probability with each sample will be chosen, because that is this probability. How frequently a particular sample will be selected if a sampling plan is applied repeatedly in the same population. Thus we can calculate the frequency distribution of the estimates. So depending on what, if we choose Si, we get a different estimate. If we choose a S3, we're gonna have a different estimate. But we know the probability of choosing Pi and the probability of choosing P3. So we can thus, based, because we know these probabilities, we can calculate the frequency distribution of the estimates. Thus we can develop a statistical theory of sampling for the procedure of probability sampling. So for example, we have a population of size 6, and it has its population units which are labeled as 1, 3, 4, 5, 6, and there they have a corresponding y which we try to measure, the population y, which is typically unknown, but say here in this case we know it. Y1 is 2.5, y2 is 3.1, y3 is 2.8, y4 is 1.9, y5 is 2.6, y6 is 2.4. Now from this we take a sample of size 2. So what possible samples, and supposedly the possible samples that we can take is only 3. S1 we can take, which is going to be 1 and 5. We can take a sample S2, which can be 2 and 4, and we can take a sample S3, which is 3 and 6. And they are assigned some probabilities based on, say, which one, which say we take a a coin toss and we say that we have an H and H, we can have four things can happen. Two coin tosses, we can have H and H, or H and T, or T and H, or T and T. If we can get H and H, then we're gonna take S1. If we get T and T, we're gonna take an S2 sample, and if we take either of these, we're gonna take a S3 sample. And obviously the probability of that is going to be 1 by 4, probability of that is going to be 1 by 2, and probability of that is going to be 1 by 4. Thus the probability of choosing the samples are pre-assigned. So now if we choose S3, then observations are going to be, so these are Y, but the sample observations are going to be Y1 and Y2, and for this also Y1 and Y2, and this also Y1 and Y2. So if we choose S3, then the samples are going to be 3 and 6, and for that we know the value of 3 is 2.8 and the value of 6 is 2.4. So 2.8 plus 2.4 divided by 2, that is going to be 2.6. So that way we know the probability of getting this sample, and we know the Y that you will get if we pick this sample. So we can estimate the population mean based on the sample mean. So in theory we can write all the SIs and their PIs, but this we can't really do this in a real world, because most of the time the n is not just 6 and the possible samples are not just 3. There are many possible samples. So instead of picking sampling units one by one till we get a sample of, we instead of using the samples, we pick up the sampling units one by one till we get a sample of size n, or we can pick them in a group. For this we pre-specify the probability of inclusion of each sampling unit. So that's the important thing, that for the probability distribution or the probability sampling, the probability of inclusion of each sampling unit has to be pre-specified. Now for a sampling strategy, there are a class of possible samples, for example S1, S2, Sk, and each of them will have a value of the estimate, which is say T. Suppose probability of choosing ith sample, say Si, is Pi, and the estimate obtained from Si is Ti. Then the expected value of the T will be given by I is equal to 1 up to K Pi Ti. Because what is the expected value? Expected value of T is the mean value that you're going to obtain from all the samples. That is the expected value of T. So if you have Si all the way up to K samples, and each of them is going to give you an estimate of Ti, so you're going to say S1, so Pi, say P1 T1 plus P2 T2 plus P3 T3 will give you an expected value of T for the population. So what it is really just a expected value is the weighted average of its value over all possible samples. So expected value is the weighted average of its value over all possible samples, and the weights being the weight being the probable of the basically just the selection probabilities. Now it is obviously desirable that the expected value of the estimator, which is t is the estimate, the expected value of this estimator is equal to the parameter being tested. So we would like that the expected value of t is equal to parameter being tested, which is given by theta, or because expected value of t is just I is equal to 1 up to k, p1 t1 is equal to theta. So what is the bias going to be? But obviously this is never the truth, so there is going to be bias. So that is what is bias. The bias is the bias in the t is the expected value of t minus theta. So the bias is how different is the expected value from your sampling procedure compared to the population parameter. An unbiased estimator will have this as 0. Now the other question is variance. So what is the variance of the estimator t for a population parameter? So variance of the estimator t for the population parameter. So variance of a estimator t for a population parameter theta is given by, because we are taking a bunch of t's, it would be estimated value of t square minus expected value of t square, because we are taking a bunch of t's and we want to see what the, if we take sample, this sample and this sample and this sample and this sample, and each of them has t1 t2 t3 t4, and you want to see the variance of this. So the one way of getting the variance is to get a t bar and then ti minus t bar, so sigma ti minus t bar. But the alternative of definition of variance is this, and this somehow simplifies into this equation, which is I is equal to 1 to k ti minus expected value of t square p. So the variance of an estimator indicates the amount of variation in all the possible values. So this is the all the possible values of estimator over repeated samples. Variation in the possible values of the estimator over repeated samples. So obviously the variance would be large if there is a large difference in the possible values, and small if the possible values are close to each other. This thing is the expected value and this is the ti. An estimator with a smaller variance is to be preferred compared to a estimator with a larger variance. So one thing is that the estimator needs to be unbiased, and the other thing is that the variance is supposed to be very low. So that is just the variance, but then there is another thing which is called the standard error. Standard error is really just the standard deviation of the estimator t, which is just an under root variance of t. So the problem with the variance is that it is the square of the unit of the target variable y. Also, the value of the variances are usually quite large. So instead of variance, we use the standard error of estimator as an indicator of its variability, which is just the square root of it. So closer the possible values of estimator are to the possible across all possible samples, and the smaller will be the standard error. Estimator has a high precision, and this question will be asked that the estimator has high precision if standard error is small. So standard deviation of the estimator t is just a variance is just a square root of the variance. Now, what is the precision of an estimator? Precision of the estimator, high precision is small, right? So precision of an estimator is inversely proportional to its variance. So when variance is small, the precision is high. So ideal situation is this, that the estimator is both unbiased as well as precise. So if it's unbiased, there is no systemic over or underestimation, and all values are close to the true values of the parameter, and all values are close to the parameter, and they are precise, meaning all values are close to each other. That is that the standard error of the estimator is low. However, sometimes precise estimator may have bias, and unbiased estimator are not precise. So if we want to compare two estimators, we don't know what to actually use, because they can be biased and precise, or unbiased and not precise. So then we use another term called as mean square error. Mean square error. Now what mean square error is, just a mean square error of an estimator t for a population parameter theta under a sampling strategy is given by mean square error of t is equal to the estimate of t minus expected value of t minus theta square. That simplifies to I is equal to 1 up to k samples ti minus theta square pi. What's the expected value of t? Expected value of t comes out from here, which is pi ti. This is the expected value of t, and we put expected value of t minus theta square, it will simplify to this equation. So MSE is the squared deviation of t from the parameter to be estimated, while variance considers the square deviation of t from its expectation. So that's the difference, right? MSE is the t minus theta MSE of t is the squared deviation of t from the parameter, while the variance is ti minus expected value of t square pi. So square deviation of squared deviation of t from its expected value. So that's the difference. Here we are considering the square deviation from its expected value. What is expected value? Expected value again is the comes out from this. That's the expected value, and that is what we use to calculate variance. But for the MSE we are considering the square deviation of it from this. So now if an estimator T for theta is biased, and expected value of T say is m, then bias of T is going to be expected value of T minus theta, or m minus theta. Variance of T is going to be expected value of T minus m square. So square deviation of T from its expectation, which is expected value is m. So T while MSE is going to be T minus theta square, and when we simplify it we can get this MSE of T is equal to variance of T plus bias of T square. So all this comes down to just this formula, which is a important formula to remember, which is this: the mean square error of an estimator T is the sum of its variance of T and the square of the bias of T, and the estimator with small MSE will have both its variance and the bias, which would be very small. So a question can be: an estimator T1 is unbiased but has a large variance, estimator T2 is unbiased and has a small bias and small variance, and we can criteria of MSE we can decide to choose the estimator even though it is a biased estimator. When an estimator is unbiased, then its variance and mean squares are equal, so it makes no difference which one we use. But when an estimator is biased, then the mean square error is a better measure to use for comparison, as a mean square error is the sum of the square of the bias and the variance. So both the bias and variance will be taken into account in the comparison.